So, welcome back. In the last lecture, we have seen the introduction to X-ray fluorescence spectroscopy, and we also saw that what are characteristic X-rays, and we also saw some examples of the characteristic X-rays. So, this lecture will be continuing the X-ray fluorescence spectroscopy. We will having two parts. First, we will see how we can quantify from this XRF spectra, and then we will introduce the XPS and the Auger spectroscopy. So, continuing with our previous lecture, we saw the X-ray fluorescence spectroscopy, what are the principles, governing principles. Now, we want to quantify. Now, if we want to quantify, how do we compare? We compare the integrated peak intensity ratios. So, the peaks wherever they lie, how are they comparing with the other peaks? So, that is called peak intensity ratio. So, the ratios will tell us what is the proportion of elements present in the sample. Okay. So, elements wet fraction C, so this is the wet fraction of the element in a mixture, will be associated with the relative peak intensity and impacted by the matrix factor and the instrument factor. So, if I combine all these together, we have this expression C is the product of M, K and IR. M, K and IR. What is K? First let us see. K is a factor which incorporates primary source conditions. So, the primary electron beam, the geometric configuration of the sample, and with regards to detection and radiation and the characteristics of detector. So, it is primarily impacting the instrument, okay, the instrument, the X-ray fluorescence spectrophotometer. It takes into account all the factors which is K. Now, the matrix factor depends on the sample which is to be analyzed. So, these are like the sample may have interaction with other elements. So, if there are elements other than the elements which is to be analyzed, so obviously it will interact with each other. So, if they interact with each other, they can have different effects, the primary absorption, secondary absorption and the secondary fluorescence. What are these? Let us see. What is the primary absorption? Primary absorption means with the radiation that it is something like that some radiation, input radiation you are supplying to the sample. Okay. So, this is suppose a sample you are supplying some input radiation. So, now while it goes inside the specimen, there may be some other radiation or there may be some other radiation coming out from the sample. So, it means those which are then absorbed while the sample enters, those are called primary absorption. What are secondary absorption? The absorptions of fluorescent radiation from atoms which transpire on its way in the sample. So, secondary means because you are sending the amount of energy which is coming out from the sample is able to excite other atoms, lower weight atoms. So, if they are excited, they will again give some fluorescence radiation. So, this fluorescent radiation will again get absorbed. So, these are secondary absorption. Then there is secondary fluorescence. The fluorescence radiation from atoms that are excited by the fluorescence radiation of the atoms possessing a greater atomic number in the sample. Now, suppose you are hitting the particular beam onto a sample which is having a higher atomic number and you have nuclei of lower atomic number surrounding it. So, it means while the characteristic escapes, it may have sufficient energy to excite the nearby lower atomic nuclei. So, that is called secondary fluorescence. The primary fluorescence radiations from heavier atoms have energy. So, that is what we imply. The primary fluorescence radiation from the heavier atoms have energy which is enough for secondary fluorescence to be excited of lighter atoms. So, obviously, heavier atoms will have a characteristic X-ray to be very very intense, and because of this intense characteristic radiation, it may excite of the nearby lower atom in the sample. So, they may emit secondary fluorescence primarily due to the higher wet atom. What happens due to this is it will reduce the characteristic X-ray line. So, see now some X-ray lines, characteristic X-ray lines are emitted from the sample. Now, some of them is absorbed. So, what happens? So, your intensity will drop down, that is what it says, that it reduces the characteristic X-ray line and secondary fluorescence leads to an increase in the intensity of the lighter element, because secondary fluorescence you will be able to excite the lighter nuclei. So, if they are excited, so they will be having higher intensity. So that is what it overlaps the actual primary beam, it will be lowered because of the presence of this secondary fluorescence. So how do we quantify? We use an internal standard method, the addition of a standard element with known concentration into the sample. So we have a sample, let us say sample S is there, and in sample you may have different elements, and suppose you want to compare a particular element. So you have to insert a internal standard which is similar to that element. When I talk about similar to that element, it means the atomic number is close to that element. So that is what you have to be a internal standard. It is assumed that the matrix and instrumental effects are the same for the reference element and the element to be analyzed. So if there is an element E1 to be analyzed and this is E2, so this E1 plus and E2 should be having similar effects. So if that is true, then the element's weight fraction Cx is obtained. So if you know the X-ray intensity of Cx, which is the element's actual element which you want to analyze, and if you know the weight fraction, if you suppose you add the particular element weight fraction and you measure the intensity, divide these, so you will get this expression. So you can find out the unknown concentration Cx. So you know Ix, you know Is, you know Cs, because these are Ix and Is you will be measuring from the spectrophotometer. Cs is the one which you have prepared. So this preparation should be not of high amount. So maximum it can go up to 10 weight percent, not more than 10 weight percent of this element which you want to analyze. Otherwise you will have some other results or distorted spectra, something like that. So this is the very simplest way to get an internal standard method to evaluate the concentration of an unknown element. Electron microscopy, what you have is, we have separate standard specimen consisting of the elements in the samples to be analyzed. Now standards are measured under the same instrumental condition as those of the sample under concentration. Now issue is, the spectra of the analyzed and the standard specimens are obtained under identical condition for these parameters. So what you do it separately. I mean, you do it one for a standard, one for the actual sample. Earlier we used to do it together in the earlier case, internal standard. Now it is separately. Now if this is done separately, so these three factors should be taken into consideration. What is that? First is the acceleration voltage of the beam of electron, because acceleration voltage will actually depend upon the brightness or the contrast of whatever spectra you are getting. So this is one factor. Then the X-ray takeoff angle. So I already told what is the X-ray takeoff angle in the previous lecture. So if this is so if the detector is here, so this is the takeoff angle. I cannot make it properly, but this is theta. So this is the takeoff angle, and if the detector is here, it comes and strike here. So this becomes the theta. So these are the takeoff angles. Takeoff angle from sample to the detector, and detector coincidence loss. It means how much time you are putting the detector onto the sample. So it depends on that time, the dead time. So dead time means the total time you actually, dead time or residence time, whatever you can say, but dead time means the total time you are actually focusing that particular detector onto the sample. So all these three factors are taken care here. So suppose if you have for a particular concentration, I means here the particular concentration of the element you want to find out, and Ci is the one which is in bracket is for the standard. So standard is Ii. Now this factor Zi, Ai, Fi refers to the metric factors impacting the X-ray intensity of the ith element in the sample Ii and in the standard Ii. Okay. So it means that you will have a factor which is Zi, Ai, Fi. If you divide them, so this concentration is directly proportional to the intensity. For the standard is also proportional divided. So when you divide them, there will be a factor Zi, Ai, Fi. This Zi, Fi needs to be actually found out. So how do we do that? We will see in the next slide. So this is nothing that the ratio of the intensities of the actual sample to the standard sample I can write in terms of Ki. So let us see how this Z, A and F are related to the elements. First Z, this Z is nothing but the atomic number effect. So what is it? It is a difference in the production of characteristic X-rays because of changes in atomic numbers in the matrix. This occurs due to the electron backscattering and the electron retardation. Now, as I told you, when a particular electron beam hits onto the surface, there will be elastic collision, there will be inelastic collisions, fine. If I can quantify them in two factors, one is backscattering, amount of electrons which are backscattered, and electron retardation. So, let us first see one by one. What is backscattering? The backscattering is fraction of primary electrons that are scattered back without generating X-rays. So, you are sending some electrons onto the sample, they are simply scattered back, elastic collisions coming out, so they do not generate any X-rays. So, whatever photons you send, photoelectron you send with a particular energy, same photoelectron you receive. So, nothing is being sent back. So, obviously, they are scattered back, and where do they scatter back from? Mainly from higher atomic nuclei. Then there is S factor. What is this S? S is the continuous loss of electron energy when electrons traverse. So, when the beam strikes on this sample, so it will travel inside the sample, but there will be loss in electron energy because on account of inelastic scattering. So, this loss is defined in this expression where rho is the density of the sample, E naught is the acceleration voltage, and S is the distance travelled. How much distance it has travelled inside the sample, this is S. So, you can see that this S electron energy is the product of the inverse of the density into the derivative of the acceleration voltage with respect to the distance travelled. So, from this expression we can say it is inversely proportional to R and both atomic number. Okay. So, that is what you have to keep in mind. So, we will have this Z factor to be very important because these two effects do actually affect the characteristic X-rays coming out from the sample. Then the X-ray absorption factor. So, what is that? X-ray absorption factor gives the reduction in characteristic X-ray density from the location of the emission to that of detection. So, how much is absorbed while on the way out from the sample? It gives that only. So, there is this expression which is given as the relation. So, amount which is coming out is equal to incident electron beam, the exponential of minus mu rho into rho t. Rho is the density of the specimen. So, this is again another X-ray absorption factor. So, it says that the characteristic X-ray which is coming out from the sample is exponentially related to the negative of the ratio of the, this is the coefficient, the absorption coefficient mu to the density of the sample. Okay. So, this is how it exponentially decreases. Then finally, we have the fluorescence factor. It refers to the excitation of the analyzing element's characteristic X-rays by those emanated from the matrix atom. So, the matrix elements emit characteristic X-rays with energies higher than that needed for the characteristic X-rays of the element to excite. So, I told you, so when characteristic X-rays are emanating from the specimen, it may excite the nearby lower atomic nuclei. So, that is what we call fluorescence factor. So, this obviously the intensity of the X-ray will be enhanced, but the unknown will somehow be decreased. So, if you want to know the spectra you will be getting is quite enhanced, but it will be primarily of the lower atomic weight nuclei. So, the now how will we do then quantify it? What we do is, if we know Z, A and F, the elements wet fraction from the relative intensity. So, you know the relative intensity of Ki. So, this Ki, see it means if you just look the previous expression, what we got is you have a relation where Ki is equal to I by, okay, the component to be analyzed by the component standard. So, now you know Ki for individual, let us say there are 3 elements, so let us say you have I equal to 3 different elements. So, you know individually what are the K1, K2, K3 values, because you will be coming to know I1, I2, I3. Now, what you do this, you can obviously get a a fraction, wet fraction. So, suppose this is Ci, okay. This Ci is then what you do is you keep it at the first calculation, Then you compute Zi Fi. So, it mean you will be having Z1 A1 F1 for element 1, Z2 A2 F2 for 2, Z3 A3 F3 for 3. So, again you compute this this Ci from this expression Ci. So, I just go back 2-3 slides, so you will come to understand. See this expression, I will just write out this expression there, then you will understand. So, it will be Ci by okay. So, once you do that, you find out Ci, okay. This Ci, so this is nothing but Ki, II, this is Ki, this is I have already written here, this is Ki. So, you find out Ci from this expression. Now, calculate separately this factor for individual 3 elements, again multiply this, then again you will get Ci. Now, you get this Ki from this expression, you will get a one Ki from this expression, this Ki and this Ki you compare with actually the one which is measured. Okay. You keep on comparing this Ki with the one which is measured. So, you will have 2 Ki until they both coincide. Once it coincide, you stop there and you report the concentration of the 3 elements. So, this is the way you do it. So, these things actually they do it directly in the spectrophotometer. So, that is taken care of. So, we complete the X-ray fluorescence spectroscopy. Now, we move on to what is the next part of our lecture, which is the X-ray photon electroscopy, which is called XPS and associated Auger electron spectroscopy. So, first we discuss XPS, X-ray photoelectron spectroscopy. Not many institutes have this instrument, because it is I mean you need a pretty higher it cost wise is pretty high, and you need a very ultra high vacuum to maintain, because here we are actually analyzing electrons, the kinetic energy of electrons. So, there should be perfect vacuum. So, that is why this instrument is in very, I mean there are, but lesser as compared to the other instruments which I have taught. So, this X-ray photoelectron spectroscopy with 2 types, the X-ray photon electroscopy XPS, and then you have the Auger spectroscopy AES, Auger electron spectroscopy. Now, what is this? So, this is some cold level, some particular atomic states are there in cold level. So, these are something which are at rest. Now, this is Fermi level. Fermi level I have already explained you. What is Fermi level? Fermi level is the thermodynamic work needed for the addition of one electron to the body. Okay. So, it means this much of energy is already it is possessing. Then if you want to take this out into vacuum, so you have to supply this much of energy, and then again another part of energy, so that it goes into vacuum. What is vacuum? The energy of a free stationary electron outside of any material. So, Fermi level means you are at a point where it is not at vacuum, but this is the amount of work you require for addition of one electron to the body. So, it means if I want to add this energy, it means if I want to give this energy, then it will overcome this Fermi level. If it overcomes Fermi level, it means I have to reach the vacuum level. So, if I write down in the form of equation, that is the total kinetic energy of this electron is nothing but the total photon which has been sent, total energy of the photons which has been sent minus this sample energy. So, total kinetic energy of this electron is the input energy minus this plus this, add these two up. So, it becomes the kinetic energy of the electron. While so, the spectrophotometer, if it starts from Fermi level, and if I do for 2 samples, one is for the actual sample, another for the specimen sample. So, it means that kinetic energy then takes up the form input energy minus binding energy for the sample energy, and then minus whatever the value which is here. This is nothing but phi specimen by phi sample. Okay, phi specimen by phi sample. So, you have to add this energy also, subtract this energy also, not add. I mean, we are adding means we are adding this, this and this. So, it means we are this total 3 parts of energies we are subtracting from the input energy. Okay. So, that is what it is. So, we are subtracting three parts: the binding energy, the sample energy, and then the difference between the specimen and sample. So, it means that if I open this bracket up, so what you have is sample, this sample gets cancelled out, what we have only the specimen energy. So, this specimen energy is something of a function of the instrument. So, this is how actually our electron is extracted from the surface. Now, in terms of binding energy, if I want to show you, see, these are the intensities of the photoelectron versus their kinetic. So, all these are orbitals 1s, 2s, 2p, 3s, like that. Huh? So, binding energy will be the highest for those electrons which are closest to the nucleus, that you must be knowing. No? So, this is suppose the nucleus. If you have an orbit here, another orbit here, like that. So, 1s, 2s, 2p. So, 1s suppose 2 electrons are there, 2s also there are 2 electrons, p there are 6 electrons. Huh? So, the electrons which are closest to the nucleus are tightly bound. So, that is why these energies are tightly bound, it means the binding energy is the highest here. Now, 2s is the next part here. 2s are somewhat loosely bound as compared to 1s. So, this is a bit, so this binding energy increases in this direction. So, you have to supply this much of energy for 2s. For 1s, the highest, this much of energy. So, now see. So, as you go outside and outside, you supply lesser and lesser binding energy. So, at 3s, you supply less. So, like that you keep on going such that you reach the valence bond. So, this will give the, from the valence band structure, you require lesser and lesser energy until you reach the Fermi level. And then from Fermi level, you go to the vacuum level, and finally, after vacuum level, the entire electron is getting extracted, or it is getting extracted from the sample. So, then this electron will have some kinetic energy. So, one, it takes apart this work function phi. Above this EV, it will have some kinetic energy. It means the electron itself is free now and it can go out of the sample. Now, while it goes out of the sample, we actually record what is the kinetic energy of this photoelectron. So, from this kinetic energy photoelectron, we back calculate what will be the binding energy. So, the characteristic values of binding energies of atomic electrons are used to distinguish elements. XPS distinguishes elements by the binding energy spectra of X-ray photoelectrons. Photoelectrons are emanated of various electron shells and subshells. The XPS spectrum plots the intensities of the photoelectrons against the binding energies. Okay. So, I thought you might understand. So, what I am going to say. So, obviously, these are the uses. The uses is it can identify elements, it can identify relative composition of the surface, and it can also identify the valence band structure. So, if I want to draw pictorially, what happens? So, this is the incident electron or photon from some source. Let us suppose it falls on the K shell. K shell is the 1s shell. So, what happens is there will be a scattered primary electron, there will be scattered primary electrons, while amount of energy, some amount of energy will be used in scattering of primary electrons, and some energy will be used in ejecting out these electrons. Okay. So, whilst this electron is ejected out, so obviously there is the atom is in the unstable position, it is in a ionic state. Now, what happens? See, this electron is ripped off here. So, the L shell electron, which is outer L shell electron, will try to occupy the K shell electron. So, while it occupies the K shell electrons, there is this process happening, electron relaxation and photon generation, because first the entire structure will relax. While it relaxes, the excess energy, which is the difference of the energy of the binding of K and the difference of L, the excess energy is given in terms of a X-ray. This is called X-ray. So, that is what is shown here, the X-ray photon is emitted. Okay. Now, when this X-ray photon emitted, obviously this electron will be vacated, there will be a vacancy. Again, this process keeps on going until the other electron from some other shell occupies, say, let us say another electron from M shell occupies the L shell. Like this keeps on happening until the entire system is in equilibrium. Now, if this happens, then we can easily study what is the ejected orbital electron. So, ejected orbital electron, we can compute the kinetic energy of this ejected orbital energy. So, if I compute Ke, the kinetic energy, if I know the input which is the h nu, so I can calculate Be. So, if I, so it means what? Binding energy will be h nu minus Ke. Okay. Or other than this, if this part is fine, there can another possibility. So, possibility is what? Now, this X-rays are emitted here, X-ray photon. Now, this X-ray photon, if it is sufficient energy, then it can take up or it can extract a electron in the valence shell also. So, it can take out another electron from the valence shell, maybe from here, valence shell, maybe from here. If it extracts out an electron from the valence shell, then that process is called Auger electron spectroscopy, and the electron which is emitted is called Auger electron. Okay. So, you should identify what is the difference between AES and XPS, is very important. So, XPS only records the kinetic energy of the ejected electron, while so XPS obviously is a function of the input energy, while AES is not a function of the input energy, because initial electron has been ejected out. So, now after ejection of this initial electron, the X-rays produced can rip off an outer electron. These outer electrons in no way depends upon the input energy. So, that does not depend upon the external energy, but the internal energy. So, this we will be looking up, the Auger spectroscopy. So, Auger spectroscopy is also useful along with XPS to identify the total chemical composition. So, XPS, this is a sodium atom. In order to make you understand what it is, so the atom which is closest to the nucleus will have the highest binding energy. See, this is 1s, this is 2s, this is 2p. 2s is somewhere here, is coming out, 2s electrons. See, this particular spectra, if I draw this, so the binding energy, see, is increasing in this direction. The kinetic energy will always increase the other way. So, it means the electrons which are extracted from the outer shell will have the highest kinetic energy. So, those with 2s or 2p will have the highest kinetic energy, but the lower, so higher the kinetic energy, lower will be the binding energy. So, in this case the binding energy will be the highest for the 1s electron, but the kinetic energy will be the lowest. Conversely, you have those which are outer shell electrons will have the highest kinetic energy. So, you should remember these two things. Outside shell electrons will have the highest Ke, lowest Be. Be is binding energy, while core electron will have the highest binding energy and lowest kinetic energy. Okay. So, it means whenever you are plotted, so this is the plot you see. So, what are these? This is one of the peak for the sodium 1s orbital. Now, what are these in between? So, it means that continuously there are primary electrons being scattered. Okay. Some may be elastically, inelastically. So, these are those. So, these, see, you are getting primary electrons, then like that. Okay. So, like this, suddenly you get a peak. It means this peak is characteristic of the particular orbital of sodium atom. Again you have another peak which is characteristic of the sodium atom, like that. Again you keep on going with lower binding energy, you will see, you know, the amount of primary electrons being scattered is lowered. See, this is lowered as compared to this is lowered. So, it means that at higher kinetic energy the binding energy also lowers down. So, again you go ahead, you get some peaks which are again corresponding or characteristic of a particular orbital. Okay. So, let us see more examples, then it will be clear. So, let us summarize what XPS means. Energy associated with X-rays are in the window of few hundred to few thousand electron volt, which are core atomic electrons. So, XPS usually determine the core atomic states in solids. X-rays of are incident on a specimen and the electrons are ejected with kinetic energy from the electronic states. So, this expression I need not explain again, I just now explained. So, binding energy is nothing but the difference of the input energy minus kinetic energy. Electrons in the valence band. So, the valence bands will have higher energy, higher means higher kinetic energy, because they are low binding and hence will have the maximum kinetic energy. Electrons in core states possess the minimum energy, high binding energy, that demand considerable portion of incident X-ray energy so as to eject electron of the specimen. So, it will have lower kinetic energy, but higher binding energy. Now, if I want to explain Auger spectroscopy, so in 2 steps, so it means something like this happening. So, this is the Photoelectron level, this is the Fermi level. So, you have valence band, you have the conduction band. So, here in the step 1, L electron drops to accommodate core level vacancy, the L electrons. Okay. So, let us say you have some H nu falling here, getting extracted, this is gone. So, if this is gone, so this electron from the L will come to occupy this K level electron. Okay. So, while it does so, it will emanate an energy and this energy will excite this, it will give sufficient energy for this electron to escape. So, this is we call as Auger electron. So, this is called KLL Auger electrons emitted for the conservation of energy discharge during step 1. So, step 1 is this one, this is step 1, okay, and step 2 is this. So, in order to conserve energy in step 1, the total energy liberated here excites the outer electron, let us say from L2, L3. L1, L2, L3 you can recollect from the previous class. I have already shown the different electronic states, the different quantum numbers N, L, M, S. So, these are L2, L3. Okay. So, what will be the kinetic energy of this electron, Auger electron? It will be nothing but the total binding energy of the K shell minus binding energy of L2. This is the binding energy L2 minus binding energy of L3. Okay. So, something is coming out here, again something is coming going from this particular L3. So, the total binding energy of L2 minus L3. So, this is the kinetic energy of the Auger electron. Or in other way, we can also see in this way the electrons with high energy in this way, again I am just repeating. So, this again is H nu. So, electrons are excited, step 2, then the electrons from L1 occupies, this is step 1, step 2. While it occupies, the remaining energy is emitted as H nu, which is sufficient, either it can be emit as H nu or it can rip off another electron from this shell, this is called Auger electron. Okay. So, the electron with high energy hits an electron in the inner shell, the incident particle energy is so large that the electron is knocked off its initial position, the atom is then rendered ionized and the atom regains its initial state with the replenishment of inner shell vacancy by an electron from the outer shell. Okay. This is called as, so we call, because since these 3 shells are involved, so we call this transition as KLL, KLL transition, KLL. Okay. So, Auger electrons are always identify these names KLL, or you have LLM, LL then M, like that, this because 3 shells are involved here. So, in this way also this is a KLL, just now I told you the difference in energy between the inner and outer shell electrons results in the emission of Auger electron from a shell or a characteristic X-ray photon. The difference in energy between the binding energies in the electronic shells associated with the phenomena gives the Auger's electron kinetic energy. So, that is same thing. So, you from this K shell binding energy you subtract this and this to get the kinetic energy of this. So, that is what I am doing. I am subtracting the binding energy of K shell minus binding energy of L1 shell minus binding energy of L23, because L23 are degenerate in nature. So, that is why it's taken up together. So, you get the kinetic energy of the Auger electron. So, Auger electron we nomenclate as KL1L23, KL1L23. So, it means that L1 electron has occupied the inner shell and Auger electron is extracted from the outer shell, that is L23. So, what is you can summarize from these spectroscopies? What is the so again I will repeat, XPS depends upon the photon input energy, Auger will not depend upon the photon energy. XPS spectra as kinetic energy scale. So, obviously XPS spectra can be recorded as on the kinetic energy scale. For this you need to know what is the input source, what is the X-ray input source energy. A comparison of the chemical state in the sample with data is gathered using a different source. A binding energy scale is reduced for the uniform comparison of chemical states. So, what do you mean by chemical state? The oxidation states, or in which particular state the element is present, that also you can find out. Because if you rip off one electron, it will have a +1 oxidation state, then you rip off 2 electrons +2. So, as you keep on ripping off electrons, as you increase the oxidation state, the 1s 2s orbitals will be more tightly packed. So, from this packing the binding energy will also increase. So, you can from this binding energy you can tell that which state it is. So, you can back calculate and tell us that whether it is +1 oxidation state or say +2, +3 like that. So, this is a X-ray photoelectron spectroscopy for this particular sample. Now, you see these are the binding energies. See what does this mean? So, it means that these electrons are scattered, these are primary electrons which are scattered. So, the detector will keep on recording these primary electrons until it will get a peak here, again it gets a peak here. So, this ln 3p half and 3p, this one are 2 peaks. So, again it keeps on increasing, the primary electrons are scattered. So, what are these? That is the background of this XPS spectroscopy actually imply the photoelectrons with energy loss. Then as you go to lower binding energy, so these are photoelectrons without energy loss because it drops down straight away to lower point. So, there are no energy lost. So, whatever photoelectrons the peak you are getting, total energy is due to the 3D 5/2 and 3D 3/2. Okay. So, likewise if you go for lower and lower binding energies, you will keep on getting the you will keep on getting and the lower binding energy, those from the outer shell. I told you those which are in the outer shell will have the lowest binding energy. So, 4D, 4P, 2P, 2S likewise. Okay. So, this is very important. So, the detector will keep on recording or keep on extracting data of the electronic energy. It is only at those positions where a characteristic peak is recorded determines the particular orbital. So, the XPS spectra manifest in ascending step-like background which increases with the binding energy. Is occurs due to the inelastic photoelectron scattering in solid and continuous X-rays. Produces a background at the region with low binding energy. Involves satellite peaks in connection with a main core level peak. So, what are satellite peaks? Satellite peaks means suppose and from the core level there is a peak which is coming out, the electrons which are ejected. So, while it is ejected, it may also excite, it may not extract, it may excite the valence electrons. So, because of the excitation of the valence electrons, while this particular electrons comes out, the valence electrons may be excited. Because of that, there is another extra peak. Those peaks are called satellite peaks. The extra peaks even is due to the interaction between a valence electron and the photoelectrons which are coming from the core orbitals. These are called shake-up satellite peaks. It will what do you mean by shake-up satellite peaks? An electron at the valence band up to a level of higher energy and loses a few electron volt of kinetic energy in the process, because if it excites the valence electron, it will lose out some energy. Because of this losing out the kinetic energy, it will depict two peaks. Now, these are the two different forms where Auger spectroscopy is recorded. It can be either be recorded in a direct mode or indirect mode. Indirect mode, it is a differential mode. Okay. So, indirect mode because these Auger spectroscopy are usually they are weak. They are weak means their intensity is weak. So, you cannot record it in a sharp manner, but if you differentiate this intensity, so the peaks are very sharp, as you can see in here. So, the number of Auger electrons ejected is much lower as compared to the scattered primary and secondary electrons. Other than quantitative analysis, direct mode spectrum is not favored. So, this is a direct mode spectrum means what? So, secondary electrons here which are discharged of a solid surface account for the background of low kinetic energy. So, these low kinetic energy electrons which are coming out here are primarily due to the secondary electrons discharged from the solid surface, while as for the higher kinetic energy electrons, the primary electrons are the ones which are the contributor, because these are discharged of a solid surface via inelastic scattering. It will comprise the AES spectrum background in the high kinetic energy region. So, these two peaks are similar, okay? They are similar. One is direct spectrum, one is indirect spectrum, that is derivative. So, in the derivative form, it is much more easier to analyze. Another XPS spectra obviously as are against binding energy. So, if I want to classify this different region, I can classify the region as core electron levels, valence level and Auger emission. So, core electron levels, see the binding energies are Auger peaks are here. These are again 1s, 2s peaks, 1s, 2s like that, 3s. So, binding energy is higher here, towards this side binding energy is higher. So, these part you will have lower and lower binding energy. So, it means the peaks which are to this particular direction, these are valence level peaks, okay. These are valence level peaks, and those which are in this at a higher binding energy direction, these are core level peaks, and the part which are in the starting, these are Auger peaks. So, this is the entire spectrum looks like for XPS, okay. So, you have to then use your insights the particular element and then see what are the different peaks we are obtaining, okay. So, it means the three levels are very important: Auger peaks, core level peaks and valence level peaks. This is for XPS spectrum of oxidized aluminum surface. The photoelectrons here ejected by PDF subshells, they are identified by a fraction number, which is Cu2p 3/2. So, if you see, say this is Al peaks, so the binding energy is less. Likewise, carbon 1s orbital peak, then you have the oxygen 1s orbital peak. OKLL, what is this KLL means? I told you is Auger spectroscopy. So, it means K level inertial orbital electron is ejected and the other two L from, so another L shell electron is filling the K shell electron, and then the outer L shell is emitting the Auger electron. Similarly, you have the KLL, the Auger electron peaks. So, this we can classify in terms of XPS peaks and Auger electrons peak. Okay, so, these are actually plotted on a same plot, the binding energy plots as you shown here, and these are the counts. What is the energy? What is the energy of the photoelectron coming out? Okay. So, now this usually in many of these, although it is not shown here, the half and 3/2 sometimes is allotted for p type orbital, 3/2 and 5/2 are for d type orbital, and 5/2 and 7/2 for f type orbital. The fractions refer to the quantum number of total angular momentum of an individual electron in the shell. This I have already discussed in the previous lecture, that how the particular orbitals are splitted, the spin-spin coupling, half 3/2 momentum, total momentum, angular momentum. So, from that you will get different peaks. Now, another important aspect is the chemical shifts in XPS. Changes in a core electron binding energy following an alternation in the chemical bonding of the particular element under consideration. So, the core binding energy is estimated from the electrostatic interaction between the nucleus and the electron. So, it means that those which are connected close to the nucleus, they will have a higher binding energy as compared to the electrons which are in the outside valence shell. So, the binding energy may be decreased by the nuclear charge electrostatic shielding, isolating it from other electrons. Addition or removal of electronic charges after changes in bonding alters the shielding. Removal of valence electron charge increases binding energies and vice versa. Okay. So, if you extract out an electron, it will obviously the binding energy will increase. So, it will be held more tightly by the nucleus. So, XPS actually is thus useful in those cases. Okay. Suppose you want to know the oxidation state of that surface, you can find out the 1s orbital energies. So, 1s orbital energy is example for without any oxidation state. A pure metal will be obviously lower as compared to a +1 or +2 oxidation state. From there you can infer that that particular element is in which oxidation state. For example, if in a carbon-carbon bond, this carbon-carbon bond, the carbon 1s orbital is held tightly 284.8 when there is carbon attached to it. But in the case of carbon oxygen bond, it is held more tightly 286.3 because of the electronegative atom. Because of this, you will get different values correspond to different attachments. So, you see now this C2P then will be CO, this CC, because this CC bond and CC and CO bond will be then different. So, if you see the counts here of the different bond, the CC bond will have the higher, will have the lowest binding energy. See CC, this one will have the lowest binding energy here, and this COC bond here will have somewhere intermediate binding energy, and as the electronegative atoms across the carbon increases, you will have higher and higher binding energy, and in this case it is much more higher because there are 3 oxygen atoms present. So, you see more the number of electronegative atoms attached to a carbon, higher is the binding energy. One is this and this. So, 4 different types of attachment, CC, COC, OCO and COOO. So, that is how we can say that this is the chemical shifts. So, these are shifted based on the atom which is connected. So, these are typical 1s orbital binding energies for organic samples. So, if it is CC or CH, binding energy is this much. If it is CN, it is this much, like that. If it is CCl, like CF, CO, NCO, like that, OCO. So, you see the binding energy increases as you go down. So, binding energy is the highest when it is carbon fluorine, because fluorine is the most electronegative atom. So, likewise this table actually gives a rough idea where the 1s, or if we get a 1s orbital peak, for example, we get this 1s orbital peak here somewhere. So, if this 1s orbital peak, we can see what is the energy, the binding energy at this point, and then we compare in this the third column. So, which is the likelihood connection or attachment. So, from there we can also tell in what is form this particular element is. In terms of oxygen orbital, now oxygen electrons are held more tightly, the 1s orbital electrons. So, in this 1s the binding energy is pretty high, almost twice than that of 1s of carbon. These observed energies will depend on the specific environment where the functional groups are located. Okay. These are is the rules of thumb. You can see these values, and then from your intuition and from your knowledge of the chemical samples, you will be able to tell what the compound is. So, for example, if you see this is an example, this is CF3 group, this is CH3 group. So, you have what different types of carbon atom. One is carbon and hydrogen is attached, one is carbon is attached with oxygen here, and carbon is attached with oxygen here as well as here. Another carbon is attached with fluorine here. In the previous slide, what we saw is that C2F is the highest binding energy, which is true. This is the C2F, is the highest. This one is the binding energy, is the highest binding energy. Then comes C2O, which is somewhere here, C2O 290. Then CH, but it is attached with the oxygen atom, so it is somewhere lesser than CC. While this one is just connected with CH, there are no electronegative atoms. So, this falls down having a lowest binding energy. So, kinetic energy will obviously the opposite of each other. Or if you want to see the chemical shift instance of oxidation state, you can find out the shift. So, different oxidation states have different shifts. So, silica, pure silica shift is nothing. but as you go with the oxidation state of 1, 2, 3 and like that 4, so your shift increases. So, from here also you can tell that which particular silica oxidation state is present from this binding energies. Or if you plot them, if something looks like this, oxidation state is 0 when there is no core level shift. As you increase this oxidation state, the core level shift increases like that. So, we have a oxidation state of SiF4. So, we have the highest core level shift. The core level shift is the shift where this is the elemental silicon, and so what is the shift from the elemental silicon? So, that is been recorded in the XPS. From there you have to back calculate and tell us what is the actual structure of the element. So, we come to the end of this chemical shift, and now what we will do is from the next class we will be studying the actual instrument, how does the instrument looks like and how it actually measures the total scattered electron energies. So, we will continue with that in the next class.